Hello, my name is Ardan Bahatopash. I am a research assistant at the University of Cambridge at the MRC Cognition and Brain Sciences Unit as a member of the Cambridge Hearing Group, and I will be presenting a project done in collaboration with Tobias Göring titled Automated Scoring of Speech Audiometry for Cochlear Implant Listeners using Artificial Intelligence and Flexible Grading Methods. When it comes to measuring hearing capabilities, there are many tests we can use. Understanding speech is one of the most important elements of everyday hearing, so certain tests have been developed to focus on that specific skill. In speech audiometry testing, participants listen to a speech utterance and are asked to repeat it back. In closed-set speech audiometry, the utterances are chosen from a limited list the participant knows. These can be digits from 0 to 9, for example. In open-set speech audiometry, there is no limit. Manual scoring takes up critical human resources, meaning fewer patients can be seen. With recent technological developments, especially after COVID, remote testing is becoming more and more popular. With participants taking these tests from the comfort of their homes, more data is being collected, but the speed of the evaluation, generating scores from these tests, is still stuck in the old days. The solution to this is automation. Automatic speech recognition models are everywhere, used to transcribe YouTube videos, news broadcasts, or even presentations such as this one. These models have so far only been using closed-set speech audiometry, however. We wish to apply this to open-set audiometry. To do so, we chose OpenAI's Whisper, which is the open-source state-of-the-art model and has versions of different complexity levels and sizes. The research questions we have are: does automated scoring allow for reliable and robust results in speech audiometry scoring? How does it compare to human scorers? And tight and loose scoring is used in clinics to account for false negatives. Can something similar be applied to ASR scoring without distorting our data? A group of cochlear implant users, 18 of them, were presented with sentences from the BKB speech corpus. We recorded their responses for over 2,000 recordings in general. We then scaled this down to 600, both to make the manual scoring a bit more manageable, but also to balance our dataset. This gave us 10 samples per location, per listening condition, per subject. The locations at hand are home and lab. The home setting is remote testing and the lab setting is in-person testing. The listening conditions refer to the fact that the participants were given 3 different types of audio files: clean, noisy at 5 dB SNR babble noise, and processed, which is noisy audio that was then noise reduced by using a DNN. We scored these recordings 3 different ways. ASR models, 7 of them were used to generate transcripts of participant recordings, which were cross-checked using the keywords of their respective sentences. People unfamiliar with these sentences blindly transcribed these recordings in a similar fashion. They were scored identically to the ASR transcripts. And finally, people familiar with these sentences evaluated these recordings in the traditional way to generate or benchmark human-guided scores. Looking at the results averaged across all conditions, we have this following plot. The y-axis is a percentage average score, the x-axis refers to the different scorers, and on the first block we have the ASR models, the second block is the human open scorers, and the third block is the human-guided scorers. We see that in the ASR models, as the complexity increases left to right, scores also increase. We see that these models perform around the same, but there is still that improvement. However, they are noticeably lower than our baseline scores. The next block is the human transcribers. These are slightly better than the models, but they still fall short of the baseline. And then finally, we have the baseline on the right-hand side. We also want to preserve subject rankings as well as matching the accuracy scores as well as we can. If participant A does better than participant B in our baseline, we want the ASR scores to reflect this. Therefore, we use each scorer to rank the participants, which we compared to baseline rankings. The intra-class correlation coefficients generated are plotted here. The more complex models, such as medium, turbo, and large, get quite close to a perfect match score of 1. In clinics, grading is done with some flexibility, and we wanted to reflect that in the scoring of our ASR models. Another issue we wanted to mitigate is the errors that might arise from scoring from transcripts. One potential issue, for example, is about homophones, 2 words that sound the same but are written differently. We also accounted for typos, as well as negligible differences, such as mismatched plurals or contractions. The scores we calculated by perfect matches are called tight, and the scores we acquired by using these rules for more flexible grading are labeled loose. In here, we can see a comparison of the tight and loose scores. We see that for each scorer, that is an increase, the ASR scores get closer to the benchmark, the human open scores increase enough for them to overshoot the baselines. The increase being this large can be explained by human errors, perhaps in the transcripts. These loose scores do reflect the baselines quite well, at least for the ASRs. And if all we care about is the score that the participant acquires in a task, these are quite helpful. If we look at the interclass correlations, we see that the subject rankings improve for our best performing ASR models, medium, turbo, and large. The interesting pattern we see here is that the human score, the human open ICC score, decreases significantly. This is potentially caused by a large number of false positives that also cause the loose scores to increase by a significant margin. What we can learn from this is that our results are quite promising, even when we look at the non-standard speech production of hearing impaired people in remote conditions. Larger ASR models do a good but imperfect job replicating baseline scores. They do a much better job preserving effect sizes and subject rankings. For clinical applications, loose scoring is a good match because it allows for overall scores to match traditional scoring. For academic research studies, where between condition effects and longitudinal patterns might be more important, the choice of tight and loose will depend on model, but we see that tight scoring generally does a really good job preserving those effect sizes and those between condition effects. Thank you for listening to my presentation, and I would like to thank everybody at the Cambridge Hearing Group for all their support during this project.